My talk today will be about the relevance of academia in a commercial world. A few words about myself in Sheffield. I've been working in the additive manufacturing, rapid prototyping industry for almost 20 years now. I'm director of the Centre for Advanced Additive Manufacturing. Just an explanation of what we mean by that is that we can clearly see that additive manufacturing is going into two directions at the moment, and I think it will do long term. The low-cost 3D printer end and the more industrial, high kind of end, okay? And it is that latter, higher additive manufacturing end that we feel we should specialize in. The 3D printer end is booming. It's doing its own thing. That's great. But when we're starting to put parts, for example, on aircraft, in cars and so on, you know, we need a bit more science behind what we're doing, and we think that's what we're good at. And certainly at Sheffield, we do a lot of work with industry, and I guess that's why I was invited to come and give this talk. So, the relevance of academia in this increasingly commercial industry. Can I just have a quick show of hands for people who currently are studying or work at a university or a school? Quick show of hands for those who are in education, academia. Okay, and those who work for companies? Okay, the majority. Okay, that's the reflection I would have expected. Now, show of hands for people who have worked in projects that have involved both an academic partner and an industrial partner. Excellent. In fact, that's as many as there are academics there. Okay, that's great. That means that we're obviously doing a lot of work between academia and industry. That is a very healthy thing. Okay, so I'm going to just talk today a little bit about academia and the birth of this industry. I think a lot of people may not realize the role of academia generally in the industry, so I'll talk about how it was born. Then I'll give some examples of how we're working. I mean, Yari gave some work today, again, that had its roots in academia. And then talk a little bit about the future role of academia in this increasingly important industry. So, quick quiz here. Does anyone recognize at least one of those faces up there? Show of hands. Okay, okay, good, right. Okay, now, those four people there are from the four perhaps key technologies that formed the growth of the birth of this industry. So stereolithography, laser sintering, fused deposition modeling, and the 3DP, okay? Two of those came from universities and two came from private industry. Is anyone brave enough to link one of those faces with University of Texas? We can go 1, 2, 3, 4. Who thinks it's number 1 who might be involved with the University of Texas? Number 2? Very good over there. Okay. You're from Sheffield. Okay, so this second one here is Carl Deckard. He was an undergraduate, sorry, an MSc student at University of Texas in Austin in the late 80s when he sort of came up with the original work that formed laser sintering. Okay. The other one here from academia is Eli Sachs on the right-hand side, who works still at MIT, and he was behind the 3D printing technology. Okay. Eli has moved on to other areas, but these guys are still all very much involved. So the other guys are Scott Crump, who set up Stratasys, and Chuck Hull, who set up 3D Systems. Okay, so one could argue that, you know, from the birth of the industry, there's sort of like a 50% key input from academia. And that's not surprising, as it was a real new thing at the time. To give you an idea how new it was seen at the time, this is a newspaper cutting from some of the work by Carl Deckard and Joe Beeman at the University of Texas from the late 1980s. Yeah, there are some remarkable things about this, not least the fact that Carl is actually wearing a tie. But one of the things here, revolutionary, machine makes 3D objects from drawings. Okay, in the late 80s, when you're putting things out in the press, you didn't even want to talk about computers. People thought computers were things that if you pressed the wrong button, it would start World War III. Okay. We've all moved on quite considerably since then, but you know, we really have come a long way in terms of society generally and where we are and you know, how this technology was in its very infancy. So things have moved along a lot, but as I say, these guys were real pioneers. And we also talk in the industry at the moment, and I'm a key advocate for using these technologies for manufacturing. I firmly believe that this is going to be, it's going to sit alongside injection molding, CNC machining as ways of making stuff, everyday stuff. And you know, I started to believe that around, you know, the early noughties. I did some costing analysis work that convinced me that that was the case, and I think that's proved generally to be right for low volume manufacture. I think that is going to change to high volume in future. But these guys, way back in the early 90s and late 80s, were already saying the same thing. You know, I personally think of myself as something of a pioneer, but these guys are easily 10 years ahead of me in terms of thinking about these technologies. And so, you know, it's really good to see them, that, you know, their dreams eventually taking shape. Okay, so that's the role of academia, key in terms of the birth of the industry. What I want to do now is to describe a number of examples where academia has been really influential in improving the technology and taking the industry forward. Now, this can happen in lots of different ways. I've picked some specific examples that I tend to know quite well, largely they're through people I know quite well. If I start talking about other people's projects and I don't know them very well, I could very easily start going wrong. So it tends to be people I know reasonably well. But even then, and they're all UK examples, but they provide a variety of the different kind of ways that universities have an influence. So this particular one, Richard Haig and Phil Dickens at the University of Nottingham in the early 90s struck up a relationship with Paul Jacobs, who was head of research and development at 3D Systems. 3D Systems at that time was a very small company based in Valencia, California, and one of the key applications that they had found for their new stereolithography technology was making investment casting patterns that could replace perhaps wax injection molded casting patterns. You know, it seemed to be, you know, the killer app of the early 90s. And this worked well in some cases. Problems that they had was that very often the stereolithography master pattern would be cased in a shell, a slurry of ceramic, and then when it came to actually heating up and burning out the stereolithography part, it expanded, it broke the ceramic shell, and you couldn't make the parts that you wanted to make. Okay, so they set a very specific challenge down to Richard and Phil for their PhD, which was to come up with a way of making stereolithography parts such that when you heated them up inside a brittle shell, they didn't break the shell. Okay, quite I guess a relatively simple challenge in terms of idea. The solution ended up being a sort of a sort of hexagonal sort of offset kind of structure that we see up in the right-hand side. When that idea first came up with them, one of them thought this was going to work. The other one thought, no way. I won't say which one was which, but it worked. Okay? And then this led to they patented this and then licensed it to 3D Systems. And my understanding now is that $150 million worth of parts are produced using the QuickCast 2 build style. When I first knew of this, it was being developed. We referred to it as Unicast, but then when it was licensed, it took on the QuickCast trade name. Okay, so that's one very specific example where a particular challenge was set. A new idea was generated. It was funded by the Engineering and Physical Research Sciences Council with cash from 3D Systems, and Nottingham University owned the patents and then licensed them to 3D Systems. Okay, another one. So actually, as I progress through, I'm going to go through low technology readiness level, tends to be the Research Council funded kind of work, and then moving up through higher technology readiness levels as we go. So this project is one that I led. So this was EPSRC funded while I worked at Loughborough University. Now, the background to this is I'd been working on making some personalized football boots, very similar to, in fact, the kind of work that Yari was talking about earlier. About 10 years ago, I had my own pair of laser-sintered personalized football boots. They felt great. Unfortunately, I was getting a bit too old to play football by that point, but I guess a little bit better late than never. Within that project, it became apparent to me that the technical capability of making running shoes with laser-sintered outsoles was there, okay? The commercial case needed to be worked on. We were and still are working on a technology to reduce the price of laser-sintered parts to make them comparable with injection molding, and that was all part of this project. And this led to us generating the idea for a project that we called Personalized Sports Footwear from Elite to High Street, okay? And the project we went through, we worked with a number of companies, including New Balance, and New Balance were fantastic with us. They were really important. We made outsoles for sprint spikes, for running shoes, and they assembled those and made some really good running shoes. But things that we could test so that our sports scientists could work out and say, is there really a benefit for elite athletes by tuning, in this case, the stiffness of each running shoe for each athlete? You know, and we proved, you know, statistically significantly, yes, you could improve like the power generation, for example, of a sprinter. So New Balance picked up on this, and at the outset of the project, this started in 2006. at which point New Balance had no laser sintering machines. They just had one 3D printing machine to make little prototypes. They had, by their own acknowledgement, next to no knowledge of laser sintering. Within 18 months of the end of this project, they had bought their own laser sintering equipment and were in fact furnishing their own elite athletes, their team athletes, with their own personalized laser sintered running spikes, okay? And they're competing in those running spikes. And so the actual statement from the CEO actually reflects exactly what we said at the beginning. We had this vision for personalized from elite to high street. And if you read his exact words, they reflect exactly what our vision was. So this was very different from the previous example. This was one where an academic group had a vision, had to go out and present it. Fortunately, we had a receptive audience at New Balance, and then it came to a successful outcome. Okay, as we move up the technology readiness levels, so this is a TSB funded project, and TSB is really to fund work where there's perhaps a partial proving of an idea and then it's taking it closer to market. In this particular case, it was colleagues of mine, Dave Wimpenny and Jason Jones, who were at De Montfort University at that time. They had the idea for a hybrid machine that did machining, laser cladding, and a surface inspection measurement, all within one machine, okay? And this is the kind of challenge where, if you go to an additive manufacturing company, they might be interested in the cladding side. You go to a machining company, got on the machining side, and so on. And it really took someone who could step back from that and not have any particular predisposition to any of those technology areas to say, let's try and bring it all together, okay? So again, they assembled a pretty impressive team of companies here, supply chain, end users, etc., and had funding from the Technology Strategy Board. The end result of it was a spin-off called Hybrid Manufacturing Technologies, and I'm delighted for Jason Jones, who is the researcher who worked on it, who's now the CEO of this company, and they launched their product only a couple of weeks ago. So this is a really nice example, again, of a project which was really from the original spawn of the idea is actually from a university. Okay. So that resulted in a spin-out company, but many of you will be aware that there are various university academics who have their own spin-out companies. One example of that is a colleague of mine called Matthew Gilbert at the University of Sheffield. Matthew is from our Department of Civil and Structural Engineering. Okay. His background is in doing the computer algorithms for what he refers to as layout optimization. This is where a computer will automatically generate optimized geometries that can make lightweight structures with maximum strength. Okay. For someone like him, he's been into this idea for a long time. He's not really an additive manufacturing kind of person in the same way that I am, but for him, suddenly additive manufacturing came along and gave him an opportunity to make the stuff that his computer software designed. For years, he had this great computer software that designed something you just couldn't make, okay? Now he has a solution there which he's been able to make various different parts. And that's been a key element for him to then look at setting up his own company, Limit State. The reason why Matthew has set up Limit State is because he has a lot of interest from companies who want to optimize their designs. But if they go to the university, it can on occasion be not quite such a quick process to get contracts arranged and to do small, quick turnaround projects. Some of Matthew's customers are working in very quick turnaround businesses that need very light parts. And for him, being able to do a very quick turnaround is really important, and he can do that through his own spin-out company far more effectively than he could perhaps by working fully through the university. Limit State also allows flexibility. For example, there was a recent TSB call that had restrictions on the way that universities could engage with the whole call. So what Matthew was able to do was to run the project through his company, Limit State. Again, it just provides a certain agility and ability to do work, particularly when it's relevant to industry. Okay, so the last of the examples that I'm going to show actually on the screen in terms of the influence of academia is a pretty non-obvious one. And this relates to some work that I've been doing, and I'm not sure if any of my colleagues do much the same. I suspect they probably do. So a few months ago, I was approached by Goldman Sachs, the investment bank, who'd learned about 3D printing. They'd seen things out in the press and so on, and wanted to get a bit of a grip of understanding a bit more detail what's going on there. They've got a number of clients that they want to try and help out. And so they started off by doing an interview, and I did an interview along with Avi Reichenthal, was also in this particular publication, just to talk about, what the future perspectives on additive manufacturing, so that the people, who do serious investments of our pension funds and the like, could get a really balanced view. I think one of the reasons why they perhaps came to me was because, being from a university, I wouldn't have a predisposition to any particular kind of technology. I should really be pretty open and have a good broad view without having any particular bias to any technology or company, and so on and so forth. So I started off by doing an interview on that particular magazine, and this goes to a lot of people. Apparently, it goes to people from the investment community, but also to quite senior policymakers and people in government, etc. From that, I've done some further work whereby the bank have asked me to convene panels of experts from different companies who will then come and talk to some of their clients and do question and answers. I've got one next week, for example, with a bunch of investors where I've assembled colleagues from different industries with a particular focus on manufacturing, and we discuss the future of manufacturing, how it's going to move forward, what the opportunities are, what the threats are, what the long-term perhaps changes to society are that influence the mindset of people who are making long-term investments. Okay, so again, this is probably not the kind of natural thing that you'd normally assume a university is doing, but it is happening, and it does have quite an important impact. Okay, my final slide of examples of how academia has an influence is intentionally blank. That's not because academia doesn't have an influence, but because a significant amount of the work we do, we have to keep confidential. Okay, we do a lot. I'm aware of work that I'm doing and that of my colleagues. I'd say probably the most exciting and inspiring work that I'm aware of from my academic colleagues is work that I can give about that much information on. Okay, so a lot of it is completely just out of the public domain, and I think the general thing is that academia is playing an important role, but perhaps it isn't seen. And that's not a bad thing. I doubt there are any actual universities who have a standout here today, but that's fine. Aside from the research and developing the technology, there's also the really important aspect of educating people. Clearly, we right through from schools, and I think the MakerBot community, the cheap printing machines that allows kids to have printers is fantastic. That really augurs very well for the future generation of manufacturing. But also ourselves at Sheffield, we've started 2 new courses for undergraduates this year. At Loughborough, we ran a few courses. There'll be other ones up at Nottingham as well. And these are really important so that our graduates, when they leave, can go straight into the companies and hit the ground running and take the technology forward. Okay, so what about the future role of academia? If we look at some of the statistics to give an idea of how many machines are bought by academic institutions, in 2013, apparently 6.8% of machine acquisitions were to academic institutions. Okay, compare that with 6 years ago, it was 8.6%, and before that, it was even more. So one might conclude from this that the influence of academia is getting smaller and smaller. Well, in fact, in total, that isn't the case. This pie is growing so much year on year that chipping a small down piece of that pie is actually an overall growth. So the activity within the academic community in additive manufacturing is growing, albeit its percentage of the total amount is perhaps getting less and less. And that's great. That's a really reassuring statistic. To go from the origins of the technology, where there's perhaps 50%, 2 out of 4 were academic influenced, to now we're talking of a small part of the market is additive manufacturing. That to me is a sign of maturity. The technology is going in the right way, and academia working very closely with industry, as evident by the show of hands. It's really working. Okay, and then who are the companies who are best placed to work with universities? There's often a perception, and I think it's right that SMEs, small companies who don't have access perhaps to expensive equipment for making parts or for analysis, etc. They are obvious companies who should stand to benefit. Like 3D Systems in the very early days, were a very small company at that time. So it's really quite surprising to see a company like Unilever make this statement. Now, furthermore, the Unilever, they're interested in additive manufacturing. They're doing a project with us. We've secured TSB funding for this. High volume, fast-moving consumer goods. people don't normally think of that as something to do with additive manufacturing. Now, it so happens we're working on technologies where we think we can drive the unit cost of parts down to be competitive with injection molding, and hence we're talking about doing this. And so in that particular case, so a company who specializes in food and that kind of thing, you might imagine that if they can see a new technology that could help them, then that's perhaps out of field for them, then it makes sense for them to partner up with universities. And to see universities is really important. But then there are other companies, like Greg talked about GE Aviation today, and another example is Philips. You know, companies who are high tech, you know, who make high added value product. You know, I visited Philips last week and their R&D, and I was really impressed with their outlook, their vision. You know, in terms of the long term, the challenges they're looking at are awe-inspiring. They really are. But even they recognize they just can't do everything. And you know, so they say university startups, suppliers and customers are all absolutely critical for them in terms of developing the new opportunities of the future. Okay, and getting the right partnerships is really key for them in terms of doing that. So from SMEs through to large, you know, global OEMs who are perhaps in fast-moving consumer goods, even to the huge companies who are very high technology, all of those have an opportunity to work very productively with academia. So I think, you know, in summary, yeah, academia has played a key role in the development of this technology from its very inception. It's played an important role as we're going through, and it's going to continue to do so. And with that, I thank everyone very much.